Okay, thank you very much, Jody and Dennis and Krishna and Josh for inviting us. We feel very privileged to be here, especially after the wonderful speakers that you had so far in this series. I'm going to start with about a 20-minute presentation of kind of a background and theoretical conceptual framing of iSSA. And then I'm going to let Brian do the bulk of the work, walking you through the code, mainly because Brian is much more competent than I am at doing so. Okay, before we start, I would like to acknowledge that Brian and I both live and work in Logan, Utah. Utah State University in Logan resides on the ancestral, traditional, and contemporary lands of the northwestern band of the Shoshone Nation. The university resides on land ceded in the 1863 treaty at Fort Bridger and other lands within our state. Today, we recognize Utah's 8 federally recognized Native nations, historic indigenous communities in Utah, indigenous individuals, and communities past and present. In offering this land acknowledgement, we affirm indigenous sovereignty, history, and experiences. And now we're going to jump right into it, and we're going to spook you with some mathematical terminology that will hopefully become clear in just a few slides. So we're starting by talking about a thing called locally biased correlated random walk, and I'm going to try and explain what that thing is. And the first thing that I can say about that thing is that it's a discrete time positional jump process. By discrete time, we mean that it's a process that happens over discrete steps in time. And in this case, we're talking about regular steps in time. So our time unit is always the same. And by positional jump, we mean that we are imagining an animal that jumps from one position to the next. It does not exist in between. So here we have a flying unicorn across a grid of habitat qualities where the darker colors might represent better habitats for the unicorn. And at t=1, our unicorn is here. And as we progress with the process to the next time step, t=2, our unicorn jumped from here to here. And then the next step, it might stay in the same place or jump again to a different position. So this is a positional jump process. This is the underlying mathematical model. And it's governed by a few things that are important to note here. First is that a jump that we will typically refer to as a step, the length of the step is a random variable. So this is a stochastic process. The length of the step is the random variable, and it is drawn from a parametric step length distribution with parameters that may depend on space. For example, the animal might move faster or slower because it encounters deep snow or rough terrain or anything else. Or time, maybe the animal moves faster in certain times of day or year, or it may be correlated with the previous step length. So we might have some temporal persistence in the behavior of the animal. So here we have our unicorn standing in its cell, and it can move to theoretically any other cell in the landscape, but our distribution of step length dictates that it is probably more likely to move closer than far away, and the parameters of this distribution, how far it will go, depend or may depend on a variety of factors, including the conditions that the unicorn experiences right now. The other component that dictates how the unicorn moves is angular deviation. So the angular deviation is the deviation in angles between the step that the unicorn will take and the step that it has taken before. If the angular deviation is very small, the unicorn tends to move in a persistent manner. It tends to move in the same direction, step after step. And again, the turn angles are drawn from a parametric distribution, a turn angle distribution with parameters that might again depend on space, time, and or the step length. So we might have some correlation between how far the animal moves and how directionally it moves. So here we have the unicorn taken this step at t equals 1, and we're now at t equals 2, and each one of these steps that it can take has certain angular deviation from the direction that it has taken before. And if this unicorn has positive directional persistence, it tends to move in the same direction all the time. We would expect that these steps here that persist in the same direction are more likely than these steps. And the last component is the endpoint, where that unicorn will end up at the end of the step. The endpoint of the step is a position in environmental space, which we often refer to simply as habitat. And what governs the decision of which step to take is how attracted or repelled the unicorn is from that position in environmental space. That's, in other words, saying that this position in environmental space is drawn from a selection-weighted distribution of available habitats. This strength of selection, how much unicorn wants to be there or wants not to be there, can again vary across space and time. So here we have the endpoints of the possible steps that our unicorn can take, and we see that some of them have bigger weights because the unicorn likes those darker habitats more, so it's more likely to travel there. And when we combine these three components, the step length and the turn angle and the habitat selection at the end of the step, we draw randomly from this probability distribution and we get the position of the animal in the next step. That's a locally biased correlated random walk. It's random because it's a stochastic process. It's correlated because it can encompass directional persistence, whether it's negative or positive, and it's locally biased because it's affected by the conditions around it in terms of where the animal wants to go. And it has two basic components to it. One that we call the selection-free movement kernel. That's those step length and turn angle. They come together into something we call the selection-free movement kernel that defines the animal's movement capacity. And the second one is the movement-free selection kernel, which is that selection component at the end of the step. So this is how we envision this process. We have two different kernels, two probability functions. We multiply those to account for the animal's actual movement in heterogeneous landscape. So, potentially very useful model for animal movement. And you might ask yourself, wow, that's an amazing model. How can I parameterize it using real data, GPS data? And the answer that we're going to provide today, which is just one of several answers, is iSSA, Integrated Step Selection Analysis. So the locally biased correlated random walk is the model underlying integrated step selection analysis. A few things about, or a few promotional items about integrated step selection analysis. It simultaneously estimates movement and habitat selection using conditional logistic regression. In it, habitat availability emerges naturally from the movement process. So the user does not have to make any decisions about what is available to the animal or not. It's an emerging property of the model. It resolves quite a few statistical issues that we have with temporal autocorrelation in animal movement data, because we're collecting animal movement data at fairly high frequency. The positions are autocorrelated in space and time. That presents some challenges that integrated step selection analysis or any conditional analysis mostly resolve. It allows for straightforward hypothesis evaluation, including pretty complex temporal dynamics, and I think that's what attracts most users to it. It allows you to formulate biological hypotheses in statistical space in a fairly straightforward way. And as I just tried to convince you, it allows for an efficient parameterization of a mechanistic movement model, this locally biased correlated random walk, which in turn allows us to predict dynamical space use patterns. So it's a projection machinery that we can parameterize using data and then use to predict future space use patterns. And this webinar is about iSSA in practice. So I'm not going to talk much more about the mathematical underlying of the theory. And both me and Brian are going to walk you through these 5 steps: sample, attribute, analyze, infer, and predict. By walking you through it, I mean that we're going to spend significant more time on some than others. And I think those 5 steps are probably common for a lot of statistical analysis, not just iSSA. And another thing that is common is that before we go to those 5 steps, we need to make sure that our data is good and solid. If there's any data cleaning to do, and believe me, when you're dealing with GPS data, there's always data cleaning to do. Please do it, whatever protocol that you choose to employ. My group uses a certain protocol that we've developed, and that is, I think, should be implemented in AMT, the package that we're going to talk about today. But I'm not here to recommend any data cleaning protocols. Make sure all the steps that you use in the analysis have the same step duration, and Brian is going to demonstrate exactly how to do that in AMT, but the assumption of integrated step selection analysis is that we're dealing with the same step duration. And consider removing non-movement steps. And we can circle back to this at the end, but this is a movement analysis, which means that it's not very well equipped to deal with non-movement data. So if you have GPS data that indicates that your animal stays in the same place for long periods of time, you might want to consider removing those steps before you put them into the analysis, and remembering that your inference is only valid for the movement parts of the analysis of the data. Okay, so our steps. We start by sampling. And in this case, what we're sampling are available steps. So for each use steps that we have in the data, those are steps that we've observed, we create a cluster that is composed of that use step and a bunch of available steps, where these available steps are randomly sampled from what we call a tentative analytical distribution of step length and turn angles. The clusters that we create using this sampling approach are often called in the statistical jargon strata. And they're going to form our basic unit of replication in this analysis. Okay, so all the comparison of what makes the animal move or what makes the animal choose a certain habitat are all done within a cluster. There are 4 possible step length distributions that you, the user, can choose to sample your steps from. Those are the exponential distribution, the half normal distribution, the log normal distribution, and the gamma distribution. Each one of them requires incorporating a different type of covariate into the analysis itself. And by the way, I didn't mention this. All of these slides, the PDF is on the GitHub. You can download it, you can save it. Don't try and spend too much time on writing things down. You have it written down. So each one of those distributions correspond, or the shape and scale parameters of these distributions could be adjusted using different covariates that we will put into the analysis itself. So step length itself, the square of the step length, the square of the log of the step length, the log of the step length. Each of those could be incorporated into the analysis, and we will show you how to interpret the coefficients that you get out of them in terms of finding out what is the true selection-free movement kernel after you've run the analysis. So these are just tentative parameters. The turn angle distribution is always sampled from a single distribution. That's the von Mises distribution. And the covariate that we will incorporate into the analysis is the cosine of the turn angle. These tentative parameters, the concentration parameter of the von Mises distribution or the rate parameter of the exponential, could be estimated directly from the data. And that's the default, I think, in AMT. When you ask AMTs to sample your steps, it will estimate them directly from the data. but you can also plug in whatever numbers you want. These are initial guesses about these parameters. And in most cases, the analysis is not going to be very sensitive to the choice of that value. There is no right number of available steps. Despite what you might have been told, you can run this analysis with one available step per use step. You probably want to run it with as many as possible. By possible, I mean as many as your machine can handle. In the literature, it's very common to see the numbers 10 and 20 available steps per use step. Those are fine. 50 is also fine. Okay, so that's the sampling process that I think has been challenging for many people. It's quite challenging to implement, and AMT is built towards making that process much more easy. The second process is attributing each step. So once we have these used and available steps, we want to attribute each one of them. We've already talked about attributing using turn angle and step length, but we also attribute using covariates, habitat covariates, environmental covariates at the start of the step or at the end of the step. And as I mentioned before, one of the advantages of iSSA is its temporal dynamics. Because each cluster represents a point in time, we can attribute steps using temporally dynamic variables. So this could be, for example, NDVI that varies across space and time. And each step, its position has its own NDVI value in space and time. Not a problem doing that with iSSA. Just to reiterate, possible movement attributes that you might want to put on your steps is covariates, the step length, the log step length, the step length squared, the log step length squared, and the cosine of the turn angle. Which ones you put in depend on which tentative distributions you use to sample your available steps from. Habitat selection is always quantified in relation to the value of the environmental covariate at the step's endpoint. So we differentiate values at the beginning of the step and values at the end of the step. And we imagine that animals select their habitat at the end of the step. That's where habitat selection plays a part here. So when you attribute a step by the value at the end of the step, that will typically relate to habitat selection. That does not mean that you cannot use environmental attributes that were sampled at the beginning of the step. But those environmental attributes are going to be the same for all the steps in the cluster, whether that is snow depth at the beginning of the step or whether it's the time of day. It's going to have the same value for the use step and all the available steps, which means that it cannot be used as a main effect on its own. There's no variability within a cluster, but it can be used as an interaction. So we can interact, for example, time of day, which is common for all the steps in a cluster, with step length, and infer something about how movement speed changes through different times of the day. We then move on to analyze, which surprisingly is the easiest part here. Our response variable is a binary 1 and 0. The ones represent used, the 0 represent available steps. We're using a conditional logistic regression. We have to define the strata, and the cluster ID is our strata. And we want to remember to include any appropriate interactions that are dictated to a great degree by the biobiological question. So for example, you might have a prediction that when animals move fast, they also move straight. And in that case, you would want to include an interaction between step length and turn angle. In this case, perhaps I sampled my steps from a gamma distribution, and I'm including the log step length and the cosine turn angle here to account for that correlation. I might have a prediction that animals move more slowly in rough terrain. So I might want to include an interaction between step length and roughness at the beginning of the step. And in this example, I included step length square, which implies that I've sampled my available steps from a half normal distribution. I might have a prediction that animals select for water more strongly when it's hot. And in that case, I might include an interaction between the temperature and water at the end of the step. In all of these cases, in 2 out of these cases, the interaction is between something that does not vary across the cluster. It characterizes all the steps in the cluster, both the use step and all available steps, and something that does vary, the step length or the habitat at the end of the step. Then we move into inference, which tends to be more complicated. It's easy to fit models. It's much more difficult to interpret them. Conditional logistic regressions are, in principle, likelihood-based models, which means that you can use all the standard tools that you all know and love to deal with models. You can use p-values, you can use standard errors, you can use AIC, you can use likelihood ratio. I'm sure statisticians will have a lot to say about the validity of likelihood in conditional logistic regression. I'm not a statistician, so I don't have a lot to say about it. But in general, it typically is considered okay. You can use something called concordance, which is the probability that a use step is ranked higher than an available step. You can also think about that as within cluster ROC AUC, for those of you who know what ROC AUCs are. Again, this is a bit problematic. It's not really clear how do we combine concordance across multiple clusters to tell us how well is our model doing. And you can always also try to use likelihood-based pseudo R-squares. For those kind of R-squares, you need to define a null model. And again, this requires some thought. It's a bit tricky to define a null model in conditional logistic regression because there's no such thing as an intercept-only conditional model. The model has to incorporate something, but you can, for example, contrast a model that incorporates only movement component with a model that includes both movement components and habitat selection, and estimate how much of to what degree is the likelihood improved by including the habitat selection. There is a little bit of cross-validation for step selection functions in the literature. It is a pretty tricky issue for the same reason that I mentioned before with concordance. It relates to within cluster prediction rather than across clusters. So it is a bit tricky. One approach that could come very useful is called used habitat calibration plots. It was developed and presented by John Fieberg et al. In this paper. I highly recommend reading this paper. It's really good. And hopefully it's going to be implemented in AMT soon, but it's not implemented right now. I think my last comment about inference is that it is highly recommended to use relative selection strength when interpreting parameters. The relative selection strength is the relative intensity of use of 2 equally available steps or habitat units belonging to different factors of environmental space or that differ by 1 unit along environmental dimensions. That's a long formal definition. You can go to my paper about RSS to read more about it, or I actually think that John Fieberg provide an even better, more concise explanation in our more recent paper, How to Guide for Interpreting Parameters in Habitat Selection Analysis. But just to demonstrate what we're talking about, this is an example from the first application of iSSA to empirical data by Christina Prokopenko in 2017. And Christina is showing here log RSS plots for NDVI. In this case, this is for elk in southern Alberta. And what's in the y-axis here is the log RSS, the log transformed relative selection strength. And on the x-axis, we have NDVI at x1, whereas we kind of determine what is the NDVI at x2. So we're comparing 2 values, one at the end of one step, the other at the end of the other step. And we think, okay, these steps are equally likely to be taken. How much, or equally likely to be taken in the absence of our focal effect, which in this case is NDVI, how much more is the animal more likely to choose the step with the higher NDVI? So this could give rise to fairly complex patterns, even if your model is fairly simple. And that's one of the reasons to use it it is the correct interpretation of these selection coefficients. And Brian is going to show us a little bit of that. Oh, yeah, I need to talk about selection-free movement kernel. So once you're done fitting the model and you get your final model, you now have all of those coefficient estimates that are associated with step length and or turn angle, and you can now use those to update the tentative parameters that you use to sample available steps. And that updating process gives you the selection-free movement kernel. And luckily for us, AMT is doing that for us. I also provided here a recipe for doing it on your own if you want. I'm not going to go over these. Of course, they're here in this presentation. They're also in the appendices for our 2021 paper, the one that Fiberg et al. In Journal of Animal Ecology. This is just a recipe of how to calculate the parameters of these distributions based on the initial parameters that you use to sample, and then the coefficients that you get out of the iSSA. And the last step is, of course, well, not of course, many of you will stop at inferring because we use iSSA to try and answer biological questions of interest, but some of you might be interested in using it to predict. We want to use that underlying model, and really the only way that we know of right now to predict spatially with iSSA is to simulate, is to take that locally biased correlated random walk and to use it as a pattern generating mechanism, an individual based model where you simulate trajectories. This figure here is taken from a paper led by Johannes Signer. This is the guy who wrote AMT and develops AMT and maintains it. And Johannes is showing us that if we have an underlying movement process and we take an integrated step selection analysis and we try to just project the coefficients across the landscape, as is often done with RSF analysis, we're getting very biased estimates of the utilization distribution compared to a simulation-based approach. So again, I'm inviting you to jump into this more if you'd like. The bottom line is that it is the appropriate way of projecting or predicting from iSSA is to simulate, and that simulation capacity is almost ready to go in AMT, but not yet. Couple of weeks, couple of months, I hope. I think with that, I will turn it over to Brian.
Okay, I just want to start out real quick by mentioning the structure of the repository here on GitHub. So you can see there's a README if you land on this page. And we've got a little bit of information about AMT and where you can find some more information about AMT. And then, so the PDF of Tal's presentation is on here. And the main script that we're about to work through is on here. And then there's this folder called Extra that has a couple extra things. So the data we're going to look at in this walkthrough is data that I simulated. And I simulated some habitat layers, and then I simulated some tracks under an iSSA. So this code is not efficient. It's more intended to demonstrate what it looks like when you generate the selection-free movement kernel and the movement-free habitat selection kernel, and then combine them. So it's very slow, and the functions that will be in AMT shortly that we have written and we're just putting some finishing touches on will be a much faster simulator. So those two things might be of interest to you. And then the other thing is just this very quick version of everything I'm going to do in the demo script in one single piped tidyverse style workflow, just to demonstrate that you can put everything together, because Johannes, when he developed the package, really followed some tidy data principles. And then there's some information about the simulated data and some updates coming to AMT, hopefully very soon. Used habitat calibration plots and the simulators. Okay, let's jump into the code. I'm sorry that this is going to be real quick. There's a lot of steps here, and I want you to see them all, but hopefully because you have the slides of the presentation and you have the code, which is, I tried to comment in a way so that you can read through it on your own, and the recording of the video. So hopefully you can go back and spend as much time as this with this as you need. But basically what I'm going to try to do in this script is work through the steps that Tal just outlined in his presentation. In particular, the first four, I'm not going to go into the predict part, but again, if you want a rough idea of how that works, check out the extra scripts. I'm going to make heavy use of the tidyverse and pipes eventually in here. We also need the raster package for some of our covariates. Of course, I'm going to load AMT and then also lubridate so that we can format some of our dates and times. Okay, the first thing I'm going to do is load in our simulated GPS data. And we're going to say that this is where I am near Logan, Utah. So we're going to use mountain time as the time zone for the timestamp. And if you take a quick look, there's only one individual in this analysis, but it's got an ID column with that individual's ID. It's got the UTM easting and the UTM northing. That's in UTM zone 12. And it's got a timestamp. Okay, so this is probably what your GPS data would look like, or at least a subset of your GPS data would look like. And then we have these habitat layers, and I'll give you a quick look at what those look like. This is a single geotiff. It's got 4 bands, so you can load that with stack from the raster package. And you'll see we've got a variable that I'm going to call forage, which we suppose our animal will select always for more forage. Something that I'm going to call temperature, where the animal is probably going to select for some intermediate value. Too hot or too cold is not right. We want an intermediate value. We've got predator density, which we're going to interpret as a risk. So our animal should always want to avoid predator densities. And then a categorical land cover variable, which I'll give some names to those categories, but these are integers in here. Okay, so the first thing to know about AMT is that the building block of everything you do in AMT, whether you're interested in fitting an RSF or whether you're trying for a movement iSSF, is to start with a track. We either call it a track XY object if it doesn't have a timestamp, or a track XYT object. So you can take your raw data and format it using the function makeTrack. So I'm going to take this GPS data that we just saw right here. I'm going to pass this to the function makeTrack, and I'm going to tell it what the X coordinate is, what the Y coordinate is, and what the timestamp column is. And then I'm also going to pass it. Let me pull this up real quick. So after you pass it to XYT, you can pass it any of your columns that you want to keep from your original data. So maybe I want to keep the ID column. I need to name that. So I'm going to say ID equals ID. Alternatively, I could also have said all columns equals true. And I would have kept all the columns from my raw data. Otherwise, it's just going to keep these 3. And I'm also going to tell it what the coordinate reference system is just by giving it the EPSG code as an integer. Older versions of AMT used like SP's coordinates systems in here, but the new versions just want the integer for the EPSG code. Okay, so that formats our data as a track XYT. If we take a look at the class of this object, we can see at its most basic, it's a data frame, and it also happens to be a tibble, the tidyverse version of a data frame. And then it's a track XY, and then most specifically, it's a track XYT. And we have, so these are S3 classes, if you're familiar with classes in R. And so we have generic functions that can handle, that know what to do when they encounter these S3 classes. So you can plot your track, and it knows to make you a nice plot of the X and Y coordinates, and you can connect the lines and see where your animal has moved. We also have a points method, so you can plot, say, one of your habitat layers and then put down the points and the lines on top of that. Okay, so now we want to go from a representation of our data as individual points to a representation of our data as steps, the straight line connecting 2 points. We're going to do that with the function steps. So if we take a look what we just did, we just passed it our track, and it took our track and it rearranged it so that now we have the coordinate, the X coordinate at the start location, and then the X coordinate at the end location of the step. Same thing with the Y coordinate of the start and the Y coordinate of the end, and the same thing with the timestamp of the start and the timestamp of the end. So we had 2 points that were in consecutive rows, and now we've turn that into, you can sort of think of that as turning that into wide data and connecting the start point and the end point together. That way we can calculate things like the step length, the absolute direction in radians, so the bearing of that step, and then the turn angle. And note that for the first step, there was no previous step, so there is no relative turn angle. But for every step after that, there will be a relative turn angle that describes that directional persistence. And then we've got the duration of the step, which, remember, for iSSA needs to be constant. So we can see here from our nice, clean simulated data that the duration of all our steps is 1 hour. Okay. Also, I just want you to note that these things have their own class, and so there's default methods for steps that are different from tracks. So unfortunately, data cleaning is an extremely important part of doing these analyses, and we're going to gloss right over data cleaning here. We don't have time to go into the details of that, but I just want to demonstrate. Imagine you cleaned your data and some of your nice regular data disappeared because you had low quality locations. So you pulled out some of those low quality locations. And I'm just going to demonstrate that real quickly by randomly removing about 5% of our data. So we've got about 95% of our data left. And you can see one of the locations that I just dropped was this 10 a.m. location on our first day. So we've got our nice hourly data, and then we've got this gap here. So if I use that function steps to make steps now, and I take a look at this, you can see that we all of a sudden have a step whose duration is 2 hours. And that's not what we want. You can see it just connected the dots between the 9 a.m. location and the 11 a.m. location because that was the next one. But that's not what we want for iSSA. So we have a function, an AMT called track resample. A lot of people assume by the name that it's doing some sort of interpolation, and it's not. It's not going to change your timestamps at all, and it's not going to interpolate your locations at all, but it's going to find the locations that have a constant sampling interval, a constant step duration, and that's specified by rate. So let me real quick grab this help file. If you look at track resample, it's asking you for a rate, which is typically a lubricate period, and a tolerance. And there's another argument for which step you want to start on. So when I say the rate is 1 hour, telling it I wanted my steps to be 1 hour in duration, but I'm willing to accept a little bit of error around that. I'm willing to accept plus or minus 5 minutes around that. So if I had 2 steps that are 55 minutes apart or 2 steps that are 1 hour and 5 minutes apart, AMT is going to say, okay, that's fine. We'll call those 1 hour steps. So you can adjust these parameters. When you do that, all that does is it adds this column called burst. And it looks through your data and it says, okay, starting here, these are all 1 hour apart. So I'm going to assign it a burst ID of 1. They're just consecutive integers. Okay, and then we get to our gap that we know we have from 9 to 10 a.m. So we've got a gap here and we start over at 11. That's now a new burst. That burst gets ID 2. And now we've got regular 1 hour intervals inside that burst. Okay, so now if we go try to use the function steps here, it's going to yell at us. It's going to give us a warning that, hey, the function steps ignores bursts. It noticed that we now have a burst column, and it's reminding you that you should use the function steps by burst, if that's what you want, but we're assuming that's what you want if you created this burst column. So now if we take a look at this, you can see at a glance, all of our durations are back to 1 hour. And you can see that our last step in this first burst is that 8 to 9 step. And then we have no 9 to 11 step. We got rid of that one. And our next one is 11 to noon. And then also note that there's no turn angle for that step because there was no previous step. So we're starting over just like if this was the first step in the trajectory, and we're making a new set of regular 1 hour steps. Okay, hopefully that's helpful. That's great when you're exploring your data. If you want to say, oh, I have different sampling intervals, let me try. I'm gonna try track resample on 2 hours, and I'm gonna try track resample on 4 hours, and I'm gonna see what the resulting data sets are that I get out to decide maybe what how I should structure my iSSA. Okay, a little bit on cleaning. That was it. So step one that Tal presented in the lecture was sample. So we need to sample our available steps. And we need to sample those from parametric distributions. Most commonly, I would use a gamma distribution for step lengths, and then you have to use the von Mises distribution for turn angles, although a uniform distribution is a special case of the von Mises. And so it doesn't matter what the gamma is characterized by a shape and scale, and it doesn't matter what shape and scale you choose. But if you want to use a gamma distribution fitted to your observed data, you can do that with this function, fit distribution. So it looks at all of our step lengths here, and it fit a shape and scale. And the same thing for the von Mises. Now, it turns out that the default for random steps, which is the next function that we're going to use, is to use as your step length distribution a fitted gamma distribution, and as your turn angle distribution a fitted von Mises distribution. So I didn't bother saving these because this is going to redo that for me. So I'm going to use this function random steps. This is going to look at all my observed steps. It's going to generate 20 random steps for every observed step, and it's going to combine them. So they're going to all be in the same data frame now. And again, this has a bunch of S3 classes that can be useful later, and we can take a look at what we got here. So our first step in our trajectory is this one right here. It gets step ID 1. And all of the available steps associated with that step also get step ID 1. So you can see we have 21 of those, the observed step plus the 20 available steps, before we get to step ID 2. And then the response variable in our conditional logistic regression will be this column case, where we have true, which is equivalent to a 1 if it's the observed step, and false if it's the available steps. Okay. This also has attached to it some attributes, including the fitted step length and turn angle distribution. So we're going to need to access those tentative distributions later, and these AMT objects keep those distributions for you handy because you're going to need them later. We also have convenience functions that can extract those for you, so you don't have to go into the attributes. You can just ask for the step length distribution of that object or the turn angle distribution of that object. Okay, and since we used the gamma distribution to sample our available steps, we're going to want to include the log step length in our analysis. So I'm going to just add that as a column right now. And then to model directional persistence, we're going to need the cosine of the turning angle. So I'm just adding those columns on. So this is what we have right now. We have all of our steps plus the log step length and the cosine of the turn angle. Okay, so now that we're done with the sampling, now we want to attribute our steps. I'm going to start with our environmental covariates, and then we're going to add time of day. So this function extract covariates is just a wrapper for the raster packages function that extracts from a raster. So I'm going to pass it our steps, and I'm going to pass it our habitat raster. And you can see that there's a bunch of S3 methods, and the one for steps includes this argument where, which defaults to end. So this is where do you want to, the step is composed of 2 points, a start and an end. Where do you want to attribute the habitat from? So I didn't put an argument here, so it's defaulting to end. So it's going to attach the habitat at the end. I could have also said start, or I could have said both, and it would have given me both the start and the end. So I'm going to extract those. I mentioned that our land cover data is really categorical. So I'm going to use factor to turn it into a factor in R. Otherwise, the model would think it was a numeric variable because it's just integer values right now. Call those grassland, forest, and wetland. And when we get to our modeling, grassland will be our reference category. Okay, so we've got all the columns we had before, and we just added on forage, temperature, predator, and not printed here, the cover category. Time of day works similarly. Time of day is a wrapper for the map tools functions that look at the time of the timestamp and the location. So it knows where you are on Earth, adjusts for the fact that times of day are different at different times of year. Sunrise and sunset are different times depending on where you are on the globe. So it extracts the time of day for you, also has a where argument, and I'm going to tell it both. So I'm going to get the time of day at the start of the step and the time of day at the end of the step. I have to make this bigger. So you can see those columns, time of day start and time of day end, are now added on. Okay, that's all we're interested in adding here. So now we're ready to analyze. I'm going to start with a very simple model and try to demonstrate the workflow for a simple model. And then we'll try the more complex version, which is actually the model I use to generate the data. So we have this function fit iSSF in AMT. That's just a wrapper for the clogit function from the survival package. It's really helpful to spend some time with the help files from the survival package for both clogit, and then it turns out that clogit is actually fit using the same routine as a Cox proportional hazards model. So if you really want to understand how to pull these model objects apart, you want to check out the information from the survival package on those. But fit iSSF, all we have to pass to it is the data and the formula for our model. And then we also need to say model equals true. You in general probably want to say model equals true for these so that you can predict later. Okay, so that's our data with everything attributed to all the steps. And then here's our formula. So the response variable is that case column. And I like to do this for myself, not just when I'm teaching, but even in my own code, I like to write out, okay, here's my habitat variables, here's my movement variables, here's my habitat movement interactions, or whatever else I have in my model. Helps keep these long formulas clear what you're doing. So we're simply going to include 2 of the habitat variables in this simple model. We're going to include the step length and the log step length so we can update the scale and shape of the gamma distribution, and the cosine of the turn angle so we can update the concentration of our turn angle distribution. Don't forget to add the strata. This goes at the end of all of your formulas. If you forget, the model will still fit. It will take it. I have no idea what it does. It goes off running and you'll get some results back and they'll be completely wrong. I wish that maybe there's an application for conditional logistic regression where you don't have strata that I don't know about, but unfortunately, it doesn't give you a warning or an error or anything. So don't forget this part. All right, I'm going to run this and lightning fast, it's done. And if we take a look at the structure of this model, the actual clogit and Cox pH model that we fit is an element of this list called model. So if you want to manipulate that model, go into that list and get that. It also has our step length distribution and our turn angle, our tentative step length and turn angle distributions. And there's a slot for some extra stuff that is currently empty. Okay, that was easy. Just like Tal said, this is the easy part. We fit a model. All we did was 1 line of code to fit a conditional logistic regression, but now we want to understand what it means. So first, we'll take a look at the summary. We have a method, an S3 method for summary, so it knows to look inside that object at M1 $model. But there are some other functions that you might have to actually ask for the model in particular. So here are our fitted betas. So the beta for forage we can see is positive. This would be the log RSS for a 1 unit change in forage. So it's positive, so our animal is selecting for forage. That's what we would expect. The coefficient for predators is negative, so our animal is avoiding predators. That's what we would expect. And then the movement betas are used to update the tentative step length and turn angle distribution. But you'll notice that these variables in particular are not significant. So we probably would expect from this that our tentative distribution is pretty close to our true selection-free movement kernel. Okay, So how do we update our selection-free movement kernel? If you have a very simple model like this, where your movement parameters don't interact with anything, then we have this real nice helper function called update SL distr that will do it for you. It will figure out what distribution you're using. It will go look for the betas that it's expecting to be named like this, SL underscore log SL underscore, and it will update that distribution for you. So here's our tentative step length distribution. It has a shape and scale. Here's our updated step length distribution. It has a shape and scale. I'm going to just throw those together in a data frame so that we can make a nice plot. And you can see that there's very, very little difference between our tentative and updated step length distribution in this case. And the same thing for the turn angle distribution. So I'm going to grab the tentative one. I'm going to use the function update TA distribution, which assumes it can find your cosine of your turn angle parameter. It will update that, and then we can plot. And again, you can see there's not a big difference between the tentative and the updated turn angle distributions, but there's a little bit there. Okay, and now for our selection-free movement kernel, we really want to use relative selection strength to interpret what's going on with habitat selection. So we have a function in AMT called log RSS that will calculate the log of the relative selection strength for two habitats, X1 versus X2. So it's the log of RSS, which is how many times more likely our animal is to step into habitat X1 than it is to step into habitat X2. So here's as an example of how we can use that. Here's a scenario. So maybe we want to ask, okay, under our model, how much more likely is our animal to step into a habitat with forage equal to 600 grams per meter squared than a habitat with forage equals 400 grams per meter squared? So I'm going to define X1 and X2 as data frames, and I have to include all of the covariates that are in the model because this is using predict. This is using R's predict function to predict from our model. So I'm going to set forage equal to 600. In this case, it doesn't matter what I set all the others to as long as they're the same between X1 and X2. So X1 is a data frame with one row, and X2 is a data frame with one row. And the only difference between those two is forage equals 600 versus forage equals 400. I'm going to use the log RSS function. I'm going to tell it which model to use to predict what X1 and X2 are. There's some structure to this object, but there's an object called df that's a data frame in there that has all the results. I'm going to pull the log RSS out of that. And I'm going to exponentiate it to get back to RSS. So our animal's about 1.5 times more likely to step into a habitat with forage equals 600 than forage equals 400. Again, there's structure in there. I'm not going to go into that too much. df is what you typically will want out of that object. Same thing, let's do it for predators. So this time I'm going to hold forage constant at 600, and I'm only going to move predators between X1 and X2. So how much more likely is our animal to step into a habitat with no predator, with a predator density of 0 versus a predator density of 5? There's our estimate, about 2.3 times more likely. And I also asked the log RSS function to calculate confidence intervals. You can do this either using a large sample approximation using the standard errors and the variance covariance matrix, or you can bootstrap this. You have those options and specify how big you want that confidence interval to be. And those will be stored as lower and upper. Sorry, again, this is all log RSS, so I'll exponentiate to get RSS. And then finally, if I want to make a figure like this, let's say I want a figure that demonstrates how selection for forage changes across the range of values of forage, I can make X1 a data frame with a bunch of rows where the only thing that varies across this is forage. And then X2, everything else is held constant. And I'm just going to compare it to the mean forage on the landscape. So when I do that, I'm also asking for the standard errors. We have a default plot function for this that makes a very generic plot. But if we want, this is plotting log RSS. I'm going to make a nicer plot in ggplot with log RSS. And here's what it looks like. So this is the mean on the landscape. There's no difference in selection versus the mean when you're at the mean. That makes sense. So they would prefer pixels with more forage and avoid pixels with less forage relative to the mean. Okay. I'm going to fit a more complex model here so that we can look at a few more interesting things. So let's say that our animal's nocturnal and that it spends its nights foraging in grasslands. So it really likes to be in grasslands more than any other land cover type at night. And it spends its days sleeping in the forest. So it prefers to be in forest during the day than any other land cover category. And let's say that it moves faster at night than during the day. That's the biology of our organism. And we're going to try to capture that in our model with an interaction between land cover and time of day, and then an interaction between the movement parameters and time of day. If you just make these interactions with factors in R's formula notation, it will give you too many levels. I think in particular because there is no main effective time of day here. And I think that that's where it messes up. So I'm making dummy variables myself here, but don't worry about that too much. Here's our model formula. Again, our response, it's a function of, I'm including all of our habitat covariates, and I'm including a quadratic effective temperature so they can select an intermediate temperature. I'm going to include all those cover terms. Grassland is our reference category, so grassland doesn't appear here. And now I'm including an interaction between the movement parameters and time of day at the start of the step. So an interaction between time of day and the log of step length, an interaction between the time of day and the step length, and an interaction between time of day and the cosine of turn angle. And let's run that real quick and have a look. There's our model summary. In the interest of time, I'm going to keep going. Okay, so when you want to update your step length distributions and you have these interactions, there's not a generic way to do it. And AMT can't really guess what your formula was for the movement model. So you have to create the betas by hand. So I'm going to just grab all the coefficients out of the model. So here's all my coefficients and they're in a named vector. And so when I want to update the step length distribution, I need the beta that corresponds to the step length distribution during the day and the log of the step length distribution during the day. In this case, because they're interactions between categorical variables, I can capture these with these parameters. So I can pull those out. And then I need to use this function update gamma, which is going to take the tentative step length distribution, which I'm just pulling out of the model. And then you have to tell it what the beta for the step length is and what the beta for the log step length is, which I just pulled out there. So we update that. Same thing for night. We update that. And I'm just compiling these into a data frame to make a plot. And so you can see here that during the day, our animal is taking these short steps. During the night, it's taking much longer steps. And in gray is our tentative distribution. So you can see how much different these are from our tentative distribution. Same thing for the turn angle distribution. We're using update von Mises here, and let's plot that. Okay, and again, so we're a lot less directed during the day. There's a lot higher probability that the animal is going to turn around, head towards minus or plus pi, where at night it's a lot more directed. Okay, finally, habitat selection. So we want to do the same thing. We want to calculate the RSS for all of our land cover variables during the day and at night. Now, because of R's recycling rules, you could very easily make a mistake if we allowed X2 to have more than one row. In general, you probably want X2 to either have the exact same number of rows as X1 or only have one row. And in AMT's function, we enforced it so that it can only have one row. So what I want to compare is all the levels of cover to grassland. So I want to say, how much do we like forest or wetland versus grassland? So that's the only thing that's changing in here. I'm just plugging the mean in everywhere else to all of our other things, creating the dummy variables just like we did above. And for X2, I'm comparing it to only grassland. but note that it needs to be a factor with the same levels. So I'm just passing it grassland, but I'm passing it as a factor that has the same levels as the fitted model. The function will yell at you if you don't do that and tell you to do that. And then we're going to calculate the log RSS. So that was just during the day. And now we need to redo the same thing at night. And then I combine them and we make the plot. So remember, this is relative to grassland. So how much do they select for grassland relative to grassland? There's no selection, right? But during the day, they prefer to be in forest over grassland, and they avoid wetland relative to grassland. But at night, they avoid both forest. Sorry, I said that backwards. During the day, they're selecting for forest relative to grassland, and they're avoiding wetland relative to grassland. But at night, they're avoiding both relative to grassland. Okay. That's all for that code walkthrough. I just want to real quick point out in the extra folder, there's a script called quick iSSA that redoes all the same things in one workflow. So we start with our GPS data, we make a track, we resample it, steps by burst, generate the random steps, extract the covariates, factor, assign the time of day, make our dummy variable, and fit our model all in one chunk. So with that piped workflow, it's real nice to be able to run through and fit this model very quickly when you get comfortable with what all the steps are. Okay, I'm sorry that was super fast, but I'm done. And we'll turn that over to Tal for some frequently asked questions.
Yeah, I won't spend too much time on that. In fact, we have wonderful questions in the poll, but I think we have at least a couple of two FAQs that are repeated in the poll several times. So I do want to touch on that real quick. Okay, so can you see my PDF here? Yeah, okay. First question, which is not touched on the poll, but is touched on by many, many users that encounter this problem and then write to me or to Brian or to John Feberg or just bang their head against the wall. It's a very frustrating issue. Sometimes we get shape or scale or concentration parameters once we adjust them after the iSSA that are negative. Now, if you look at those distributions, they cannot have negative parameters. Their parameters is bounded by 0. So that doesn't make any sense. So how do we make sense of that? First of all, if the von Mises distribution has a negative concentration parameter, this is an interpretation that Brian came up with about 2 years ago, and I tend to agree with. If it has a negative concentration parameter, that typically means that your turn angles are concentrated around pi rather than around 0. In other words, the animal tends to turn back much more often than it tends to continue straight. Because when the implementation of iSSA, the standard implementation is that we assume that the mean direction of the turn angle distribution is 0. But if we get a negative concentration parameter, that tells us we should have assumed that the mean direction is pi, in which case the concentration parameter tells us to what degree does the animal tend to turn back, rather than to what degree does it tend to move in the same direction. If the shape or scale parameter of any of the step length distribution is negative, that's slightly more sticky problem. It's not just up to interpretation. We have to fix that. Basically, it tells us that the model is ill-fit. Something has gone wrong. And there's various ways of trying to deal with that. I listed them here by order of what would probably have the least impact on your analysis, or mean losing least data. You can try different step length distributions. So maybe you tried it with exponential distribution and you got a negative rate parameter. And if you tried with a gamma distribution, that would resolve the issue. You can include an interaction between step length and turn angle. We mentioned that before. Animals tend to be in a certain behavioral state for a while. So they might be in a mobile state where they move faster and more directionally. That captures some of that variability and makes the distributions behave better. You might include other step length interactions, such as the habitat at the beginning of the step. You might, again, want to remove non-movement steps, where basically the model is trying to fit a distribution of movement where it has this zero inflation of zero, very close to zero steps. And you might want to just resample your data into a coarser temporal scale, and that would often resolve the problem, but that also results in losing data and losing resolution. How can I combine data for multiple individuals? There's various ways of doing that. In general, I would say that if you don't care about the individual identity, if all you want is population level inference, as long as you have a balanced design, so all individuals have the same number of use steps, you can just throw them all into the same model. Again, inference is done at the unit of replication that is a single cluster that's already matched, used, and available. So we're not mixing and matching used and availability across individuals here. That's not a problem. If you would rather to take the mixed effect approach, Stephanie Maff had a really nice paper in 2020 about using Poisson regressions for estimating these models. And if you use a Poisson regression, that lends itself much more easily to a mixed effect approach, so putting random effects. And there's this two-step approach that I tend to use because I'm too lazy to try and understand Stephanie Maff's brilliant statistical derivation, and that is to fit individual models and then make inference based on those individual models. In that case, you would want to propagate the uncertainty that you have in the parameter estimates from these individual models. And there's typically two ways of doing that. You can either do a bootstrapping, where you weight the bootstrapping by the standard error or by the AIC weight of the model, or you can do a linear model where your response variable is the coefficient and you have weights that are inverse variance weights. And I provide some examples of papers that actually use those methods. I'll skip this. Yes, you can and should use iSSA with behavioral state assignments such as the HMM that we heard Theo Michelot talk about in the last seminar in this series. Typically, this is done by first fitting the HMM, segmenting your data, and then fitting a separate iSSA to each behavioral state. And you'll make your inference based on the iSSA within behavioral state, and that's conditional on the inference that you get from the HMM. And again, I'm providing here an example for a paper by Simona Picardi that just demonstrated how to do that. Okay, that's it for FAQs. We have a little bit of time to go over the wonderful collection of questions that we have.
All right, thank you very much, Brian and Tal. So I'm looking here at the website with the questions. The first question is there a way to spatially constrain where available steps may be generated? For example, when you're modeling an urban species and you want to prevent available steps from ending on a building.
Yes, there's two ways of doing that. You can include the building as a covariate, and you should get very strong avoidance. If your urban species never step on a building, you should get a very strong avoidance response. Or you can just sample your steps and then eliminate all the steps that have ended in the building. That's in a Poisson process terms, that's called thinning. So you're thinning before you're fitting the model. I see no reason why that shouldn't work. You're just making the assumption beforehand that the species can't occur there. And that's true not just for building, also for terrestrial species in water or the other way around.
Mm-hmm. And I think you alluded to this in one of your frequently asked questions. So the next question is if there's a way of incorporating random intercepts and slopes in your framework, or do you always estimate models for each individual separately?
Yeah, so as I mentioned, there is a way with C-Logic. It is a bit tricky. Terry, the developer of the survival package in R, has been working on it, and they have a couple of papers about it. There's a problem with estimating the standard errors when you do conditional logistic regression with random effects. The more straightforward way of doing it is following the MUF method, which is estimating these models using a Poisson model, where the random effects come in much more naturally. Yeah, so there is a way of doing that. My go-to is typically to fit individual models and then do stats on stats, but I know a lot of people don't like that.
Can I add one thing to that? A lot of times you'll see there can be clustering between individuals. So sometimes you'll see, like in our example of grassland and forest, maybe you have some individuals that like to select grassland and avoid forest, and some individuals that select forest and avoid grassland. And when you see that clustering between individuals, like a random slope doesn't capture that well. When you have like they're not randomly distributed, they're not normally distributed. The selection weights aren't normally distributed around some population mean. So a lot of times the random slope model, you want to be careful. The random slope model might not be a good model for what you're trying to measure.
And there's a question here that I believe you have answered. So is it possible to run the integrated step selection model per different behavior? So separating resting from traveling as a first step. So I think that's what you were alluding to when you talked about maybe running the hidden Markov model, identifying the different behaviors, and then sort of analyzing separately, right? And I think the question is, well, could you, instead of doing that, maybe, let me see, using as an interaction with other covariates, maybe adding the behaviors as as a covariate interacting? That's what I understood. I'm not sure.
Yes, you can add the behavioral classifications. If you have per step behavioral assignment, you can add them as interactions into the iSSA. You need to be careful there that the behavioral assignments are already based on the geometry of the path. And now when you're including them in there, you need to be careful not to overinterpret what they mean. You will obviously find that if you had, a more mobile behavioral state and a more sedentary behavioral state, you will always obviously find that the more mobile state has longer step length distribution. That's circular inference. But you can try and make inference, for example, about the habitat selection strength of these different behavioral modes. I think the ideal situation is to make inference about both things simultaneously. I don't know of a very smooth application of that, of kind of incorporating the HMM likelihood and the iSSA likelihood into one combined likelihood that you can iterate over. I can imagine how someone can write that on their own in R as a Bayesian model or even a non-Bayesian model, but it's not going to be something very trivial.
So the most straightforward way is really sort of doing it separately, running the hidden Markov model first, separating the data sets, and then giving independently the data sets for the integrated step selection and getting the results that way. Exactly.
Or trying to account for as much of behavioral variation in the iSSA itself and just not doing the HMM at all. So for example, that step length turn angle correlation is basically a continuous behavioral state. We assume that there's some wave of behavioral state that where the animal tends to move faster, it also moves more directional. So it already aggregates some things together, but it's a different approach than the HMM.
Yeah. And so one more question here is, what is the main difference between resource selection function and step selection function? Which method should I use to analyze GPS animal movement data if I want to draw population density map from different individuals?
So that's a huge question. Resource selection functions is a general term that is used for many things in the literature. I will assume for now that we're all talking about exponential resource selection functions with used available data, which is the most common application in GPS data. In that case, the difference between step selection and RSFs is that RSFs assume that any point within a user-defined availability domain is available to the animal at any point in time. Whereas an iSSF defines the availability based on where the animal is and when it is. So in SSF, availability is conditional on space and time. In RSF, it is not. That means that the inference that you get out of these two approaches could be significantly different. RSF, so RSF relies on a much more strict assumption, right? The entirety of space is available to the animal can jump anywhere. Given that assumption, it is much easier to generate maps from RSF than from iSSF. If your objective is to generate density maps and you don't feel like diving into simulating locally biased correlated random walks, you might want to choose RSF despite this very restrictive assumption.
Great. So Fierberg et al. 2021 recommends using infinite weighting when using RSF and SSF, but it looks like it is decreasing deviance explained of the models, apparently based on how weights are implementing the deviance formula. Is cross-validation a better way to assess model fit? So I guess I'm wondering if the question is choosing between those two and comparing deviance, perhaps?
So yeah, I think there's some confusion there, and I'm not sure I can get a straight answer. For RSFs, where the analysis is not conditional, the formal recommendation is to put infinite weights or close to infinite weights on the availability domain. This is because we're estimating a Poisson point process, and we're trying to say what we define as availability we're not estimating the true absolute intensity of use. We're estimating a relative intensity of use. In a conditional analysis, that argument does not necessarily hold. I've never tried putting weights on available steps in conditional logistic regression. I'm not sure it's even possible. I'm not sure how to derive the likelihood under that. So I think if in the Fierberg paper, we recommend using weights, and it implies that you should use weights in SSF, I think that's a bit misleading. You should definitely use weights in RSF. I think in SSF that could create some problems.
Great. We are close to 1:30. I think there's time maybe for one more question. And the question is SSF adapted for big data sets with more than 1 million locations and more than 100 individuals? Running conditional logistic regression with mixed effect framework with such large data sets seems not feasible. Is that right?
I would guess that using GLM-MTMB, which is what people use for the Poisson version of this model, the MUF method, is going to be very difficult with this size of a data set. I think you should be able to fit individual models, not a problem. So just to clarify, conditional logistic regression, the way that it's implemented in AMT, as Brian mentioned, is a wrapper for C-logit in the survival package. That function is based on a Cox proportional hazard model. And I'm saying all that just to say that it's incredibly fast compared to most things that you can imagine. Models fit really, really fast, even with a lot of steps. So when you're not fitting mixed effect models, when it's a single individual, those models fit very fast. And I've fitted models to collections of hundreds of individuals and just, put aside the parameter estimates, and then you can do a secondary analysis on that. But as a mixed effect model, I don't know. There was also a question in the questions about the possibility of doing parallel computation with iSSF. In theory, because each one of the clusters is a standalone unit in replication, you can do that. I think you need to be very careful about the implementation. Because the likelihood is calculated based on the product of the likelihoods across all of these clusters. So I'm not sure exactly how that would work.